Hello and welcome to the Daily Space. I am your host, Dr. Pamela Gay, and I am here to put science in your brain. Sometimes I look at observational astronomy results and realize I have no idea why the universe does some of the things it does. And I am really glad I am not a theoretical astronomer and responsible for figuring out some of these mysteries. Using archival data from the Arecibo Radio Observatory, astronomers have revisited an idea from the 1980s. In 1983, Michael Fall suggested that the amount of mass tied up in a galaxy's stars and its rotation rate should couple. I'm specifically saying stellar mass, not total mass of the galaxy. The idea is the more mass in a galaxy is in stars, the more angular momentum it's going to have. This is a weird new version of the rotating hoop versus rod versus disk problem from physics. Anyways, while this idea was put forth in 1983, we didn't have the ability to actually sort out if Fall was right until now. And graduate student researcher Jennifer Hardwick looked at 564 galaxies using Arecibo data and images from optical surveys. And she found that yes, there is a relationship. And as the amount of mass tied into stars goes up, the angular momentum of how the entire galaxy rotates goes up. This raises a whole lot of questions that go back to all the reasons college students hate angular momentum and calculating moments of inertia, and tells us the gas evolution of a galaxy makes things a lot more interesting, or at least a lot more complicated than previously thought. With the loss of Arecibo, it will be another many years before this work can be advanced too much more. We need to wait for the Square Kilometre Array and other next-generation telescopes to become active before we can fully understand this problem. In a lot of ways, astronomy is nothing more than the study of how mass keeps getting redistributed over the history of the universe. And it is in the surprising ways that mass congregates that some of the most interesting stuff is found. Back when I was in grad school, it was discovered that more or less, the orbits of stars and the bulgy parts of galaxies is directly related to the size of the supermassive black holes those bulgy bits contain. But then, every once in a while, a system comes along and refuses to follow the rules. In a study of the nearby dwarf galaxy Leo 1, researchers from the University of Texas, my alma mater, they recently discovered a black hole nearly the same size as the one in the core of the Milky Way. The bulgy bits of Leo 1 are a lot smaller than the bulgy bits of our galaxy, and the two should not have similar sized black holes. Research led by Maria Jose Bustamante states simply, there is no explanation for this kind of black hole in a dwarf spheroidal galaxy. This work is published in the Astrophysical Journal and is going to force folks to spend the next many years trying to figure out how in the universe this can happen. The universe really is more creative than we are, and it does some interesting things. But for all the things we can't understand, there are still some cool things that nicely match with expectations. And we're going to end this segment with one of those pleasing results. Researchers led by Takashi Shimanoshi used the ALMA, the Atacama Large Millimeter Array, to look for stars forming in the outskirts of the galaxy. These outer suburbs are largely untouched by the materials formed in generation after generation of stars in the inner regions of the Milky Way. And any stars forming will act more like stars in the early universe than like the enriched stars we see forming nearby. And researchers found a star forming in these outer reaches, and thanks to the amazing powers of the Atacama Large Millimeter Array, researchers could measure carbon, oxygen, nitrogen, sulfur, and silicon-bearing molecules, including complex organic molecules. This demonstrates that even in the most remote and raw regions of our galaxy, there's the chemistry needed to build prebiotic molecules. This further indicates that while heavy elements are more scarce in the outer galaxy, complex chemistry can still find a way. According to Shimanashi, the interstellar conditions to form the chemical complexity might have persisted since the early history of the universe. I once thought that maybe life on Earth was as old as life in our universe could be because it takes time to build the stuff of worlds and people. This research shows I was wrong and makes the question of how common is life even more interesting to consider. After the break, we'll be back to discuss how Earth's geology can muck up humans if we don't plan ahead. Stay tuned. Several years ago, I was able to travel to Lisbon to work with the Galileo teacher training program. Sitting in a small cafe, I was struck by the beautiful wreckage of an old cathedral. When I asked my collaborator about it, she told me a story I'd never heard. In 1755, an earthquake struck the region, shaking the landscape for more than 3 minutes, with a quake estimated to be between magnitude 8.5 and 9. With an epicenter located out to sea, the devastation didn't end with the end of the shaking. It was followed by a tsunami, a hazard unfamiliar to Europeans. According to historical reports, water retreated from the Rio Teja estuary and revealed shipwrecks, leading to thousands of confused people racing into the waterway in search of treasure. Unfortunately, a 9-meter wave was on its way, and thousands of people who survived the quake were lost in the water. The earthquake was on the Azores-Gibraltar fault line, and there is no reason to believe such an event can't happen again. That devastated cathedral I could see from the cafe was a reminder. Our world is alive and will destroy even the most beautiful of human creations without thought or care. And we really need to plan for these events everywhere, and not just in the most active areas of our world. During the 8th European Marine Board Forum, they focused on supporting the ocean decade in Europe, and researchers began work on the now published position paper that lays out things governments and corporations need to think about as we build and maintain global infrastructure. As an astronomer, I was unaware of all the ways planetary geology can wreck our daily lives. Beyond the understood issues of earthquakes and volcanic eruptions and the tsunamis they can trigger, researchers also detailed issues with things as mundane as the slow migration of sandbars across the ocean floor. While generally of concern only to navigators, these shifting sands can shift onto underwater cables and pipelines and potentially damage them, to the point of maybe even potentially cutting off internet between continents. Study organizer Hydram Kopp puts it this way: the probabilities with which geological events such as earthquakes or volcanic eruptions occur have not changed over millions of years, but the magnitude of damage is increasing because coasts are becoming more densely populated. We have built ports and industrial facilities on the coasts and on the sea floor, and we've generally accumulated large values there. It is stated in a press release from Geomar at the Helmholtz Center for Ocean Research in Kiel that there is still a considerable need for research to better assess geological hazards in Europe's seas. For example, there is still no high-resolution map of the sea floor that accurately shows the geological fracture zones and margins of the continental plates where earthquakes often occur. Put another way, we need to develop the kinds of ocean floor maps that we have for land. Unfortunately, studying the sea floor is something that is significantly harder and can't be done with a few well-placed sets of satellites. While we remain years to decades away from the kinds of ocean maps many might wish for, We can now focus on planning how we'll recover when, not if, the next disaster occurs. For Europe, at least, there is a clear understanding that folks will help each other, with COP explaining, if a natural disaster were to occur on Europe's coasts, all European Union states would be involved, both in disaster relief and in financing reconstruction. Our world is changing, and we need to be ready. And as we'll discuss in the next segment, at least some of the changes experienced by life can be matched up with things like variations in Earth's orbit. Stay tuned. The Earth is the only planet we can currently explore in detail, and with almost 5,000 planets known, that is pretty frustrating. At least we have this one. And while using it as a lab experiment, interdisciplinary teams are forever finding new and creative ways to understand our world's past, as we wonder if what has happened here has also happened out there among the stars. One of the harder things to study is the effect of the Earth's slowly changing orbit on the slowly changing life it carries. Evolution is a driving force of change, and local effects over the short term often dominate over the millennial changes of orbits. To figure out if the orbital changes do have an effect, researchers turn to an ancient constituent of plankton, coccoliths, to see if they record changes in their nearly 3 million year fossil history. These tiny life forms build up limestone plates called coccoliths that get left behind when the algae die. According to a new paper in Nature, researchers looked at more than 9 million coccoliths that had been deposited on the ocean floor over 2.8 million years. And they examined them for changes over time. And this work was possible only because we have automated microscopes and advances in computer vision that allowed most of the data to be classified by software. With this amazingly long baseline, researchers were able to find patterns of change over 100,000 and 400,000 years, with the pattern being one of a change in diversity. Over time, researchers noticed the diversity in sizes of coccoliths changed, with the little critters sometimes being all about the same size and sometimes coming in a large range of sizes. The 100 and 400,000 year change aligned with the Earth's variation in orbit as it wanders from having a very circular orbit like we have now to having a more flattened orbit. With a circular orbit, the equatorial regions of the Earth experience little seasonal variation, and the winter in the north is no different than the winter in the south. When the orbit is more elliptical, the seasons are more severe and vary more between hemispheres. This diversity of global weather is believed to lead to a greater diversity in coccolith sizes, but an overall decrease in the amount of limestone shells. And it turns out this diversity in how and how many coccoliths were formed may have further influenced the environment. According to a press release from the French National Center for Scientific Research, due to their abundance and global distribution, these organisms are responsible for half of the limestone, the calcium carbonate, partly composed of carbon, that is produced in the oceans and therefore play a major role in the carbon cycle and in determining ocean chemistry. It is therefore likely that the cyclic abundance patterns of these limestone producers played a key role in ancient climates and may explain hitherto mysterious climate variations in past warm periods. In other words, in the absence of ice, the biological evolution of microalgae could have set the tempo of the climates. It's amazing to me that such small critters, if you can call algae a critter, can be responsible for so much science and have so much influence. This is your reminder that even the smallest among us can have a mighty impact. After the break, we're going to be back to look at a mighty comet. All right, here we go. This week in What's Up is not another moon phase or meteor shower, but a comet, specifically Comet C 2021 A1 Leonard. If you remember last spring's Comet C 2021 F3 Neowise, otherwise known as Neowise, this comet will be like a slightly fainter sibling for now as it nears naked eye visibility and becomes an easy binocular or small telescope object as it gets closer. To find it this week, look between the end of the handle of the Big Dipper asterism towards the bright star Arcturus. As they'd say in a planetarium, arc to Arcturus. Comet Leonard will be in between the last handle star and Arcturus. As the days go on, it will continue heading horizonward. Tomorrow, December 3rd, in the morning UTC, the comet will be less than a degree from Messier 3, a bright globular cluster in the constellation Canis Venatici. A Telrad finder, this is a specific brand of finder. It can help you find the comet and many other objects using the concept of star hopping. I have to admit, this is my favorite accessory in astronomy, other than a pair of binoculars. Using a Telrad, you can go from one bright star to another star, a dimmer star, one star at a time, so you can find your deep sky target. The Telrad has what's called a reticle, a set of concentric rings that appear as red glowing circles that are 1/2 degree, 2 degrees, and 4 degrees in size. And their red light won't cause you to lose your night adaptation. This device is simple to attach to your telescope using an adhesive base. You can get more bases to use the same Telrad on different telescopes. You can get a Telrad site from Amazon, and if you use the link in our show notes, you can even support us through the Amazon affiliate program. To track this comet through the sky over the next year, you can use the free astronomy software Stellarium. This is a powerful tool for planning observing sessions, and it includes plugins for plotting different objects from asteroids to satellites. You need to point the software at an updated source of orbital elements since this is a new comet. And Stellarium makes this a simple process. The details will be at a link in our show notes at dailyspace.org. Stellarium has a mode that projects the 3 rings of the Telrad site on the simulation, so you can determine what way you need to move your scope and by how much you need to move it to find objects. The comet is moving fast. It's going over 250,000 kilometers per hour. However, it doesn't look like it's going fast because it's still very far away. Once you find it, make a note of where it is. Then after 10 minutes or so, look at that position of the comet again. There should be a noticeable difference in position. Comet Leonard was discovered by astronomer Alan Leonard on January 3, 2021, using the 1.5 meter Cassegrain telescope at the Mount Lemmon Observatory north of Tucson, Arizona. Currently, it is visible in the northern hemisphere in the morning through a telescope only. It's about magnitude 10, but in early December, it will become visible in the evening sky and will brighten to unaided eye visibility, about magnitude 4. Its closest approach to Earth is on December 12th, and it will reach its closest point to the Sun on January 3rd, 2022. Comet Leonard is what's known as a long period comet, about 80,000 years according to the Jet Propulsion Labs. It spent the last 35,000 years heading back into the solar system from the furthest point in its orbit, about 3,700 times the distance from the Earth to the Sun. Its most distant point, its periapsis, or closest point of its orbit around the Sun, is about halfway between the Earth and the Sun. This will be its final approach to the sun, as the energy it gets from the approach will accelerate it beyond solar system escape velocity. Over the next few thousand years, it will head back out of the solar system, never to return. This is truly a once-in-a-lifetime opportunity, at least with this comet. And this has been The Daily Space. You can find out more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to your donations. If you like our content, please consider joining our Patreon community at patreon.com/CosmoQuestX.